Recorded. Okay, so hello everyone. So we are going to have the second part, second lecture today. So this is basically abstract index theory. So today is going to be, so let me get my own camera, I guess. Somehow I don't have, okay, so this is, how come I have just your picture in my thing, Nathan? I don't understand.
Just have mine.
I have only your picture in my screen. I don't have, do you see my, do you see the thing here?
Yeah, I can see you. Do you see like above my picture, there's like several like collections of.
Yeah, I have to, I don't know. I think this is funny. I don't know what's going on. So I just have your picture in the camera. I mean, I want to have the board projected on my screen here. I don't know.
You have smaller pictures of all of us along the top of the screen?
I do, yeah.
If you hover over your own picture, there is this button that appears in the top right with 3 dots on it.
Yes, I do. Okay.
You can click pin video. That should make it big.
What's that?
There's a little button in the top right that appears.
Yeah.
If you click that, you can click pin video. That should make you the biggest.
Oh, okay. Yes, that's right. Very good. Yeah, I think I want to have that. Okay, very good, because that's that helps me to understand what's recorded, what's not. Okay, sorry about that. So so this is about analytic aspects. So last week we discussed purely algebraic aspects. That's quite useful, but not enough. So we're going to have these analytic aspects now. So there is, okay, anyhow, so there is a comment in the chat. Hi guys, I have to type today as I'm on different device this time. Okay, okay, good. Right. Okay, so okay, so the best now is to start with compact operators. So these are analytic analogs of finite rank operators that we discussed last week. So my notation is going to be like this. So I have H always denotes a Hilbert space. So my Hilbert spaces are going to be over complex numbers. It's not absolutely necessary all the time, but at some crucial points, of course, it's very important to be over complex numbers. So let's just assume they are over C, although some parts of the theory can be developed over real vector spaces too. As far as the dimension of the vector space goes, I don't want to assume it's countable, dimensional, or uncountable, or non-separable. Separable or non-separable, doesn't matter for most of the things, but at some places we have to assume it's separable. But right now it doesn't matter. So consider a bounded operator. So we are looking at bounded linear operators. So I don't have to define bounded linear operators. I assume you all know what bounded linear operator means. So this bounded linear operator is called compact. If T of B closure inside H is compact. So B here is the unit ball. Of H, which is the set of all X in H such that norm of X is less than or equal to 1. Okay, so so it just the definition says that the image of the unit ball may not be compact, but its closure is compact, and everything here in norm topology. So when I don't say anything else, it just means closure and topology with respect to the norm topology on H. Okay, so this is definition. It's not quite clear what definition really means right now, but immediately you can see that this definition is equivalent to it's easy to see that if and only if T is compact, if and only if for any bounded sequence in H, there should be a convergent subsequence of images of T. So xn's are just bounded, so there is no reason T of xn to be convergent. But there is a subsequence of T of xn's, say n from 1 to infinity, such that it's convergent. Because this is in T of B closure, and there is a convergent subsequence here for any sequence there because of compactness in norm topology. So this condition and that condition are equivalent. So now, so as far as examples, the easiest example is, of course, finite rank operators are compact. This we are just using a result that the unit ball of a finite dimensional Hilbert space is compact. Of a finite dimensional space is compact. In fact, the unit ball is compact in Hilbert space is compact if and only if the Hilbert space is finite dimensional. So that's something that we know from basic analysis. So these are certainly compact operators, but the question is if there are compact operators which are not finite rank. The answer is yes, there are many. So let me prove a lemma first. I mean, I'll just sketch the proof, but the idea is clear. T is compact. If and only if T is equal to limit of Tn, where Tn's are finite rank. So in other words, compact operators are exactly those operators that are limits of finite rank operators. So idea of proof in one direction. So assume T is compact. Then for any n bigger than or equal to 1, we can choose a sequence. I mean, sequence of points, x1, xn, in the unit ball of H, such that if you look at this T of x, T of xn's, every point in the image if at a distance of at most 1 over n from that set, right? So we can just say for any y belonging to B, such that for any y belonging to B, there exists n such that norm of T of xn minus y is less than or equal to 1 over n. Okay, so maybe I should say there exists I, one of I between, of course, n and y. So that's because of the image is pre-compact, so we can just choose this net of points, set of points, so that's that property. Then we can take the projection onto the image of these subspaces generated by this thing. So let Pn equal to projection onto span of one xn, linear span of these things. So it's a finite dimensional subspace, it's closed. So there is a unique projection operator onto this subspace. Then because of this property, then norm of Pnt minus T is less than or equal to 1 over n for all n. So this Pnt now is a finite rank operator because Pn is finite rank. And you know that if you multiply finite rank by anything, it's going to be finite rank. So this guy is finite rank. So this is finite rank. So we can say that T is equal to limit of Pnt as n goes to infinity. So at least this proves this in this direction, that if T is compact, then it's limit of finite rank operators. Now, the other direction is not difficult either. We just have to use this counter diagonal type arguments. For the other direction, I just mentioned it like this. For converse, use a counter diagonal argument. So you choose sequences of sequences, and then you choose the diagonal, and then that's going to give you compactness of the limit of finite ranks. Okay. So this result is really a fundamental result. It shows the relation between algebraic theory and analytic theory. The replacements of finite rank operators, which are compact operators, are exactly limits of finite rank operators. So this is something that shows the role of topology and analysis in this whole theory so far. Okay, any questions or comments? Okay, so now using this lemma, we can give examples of compact operators which are not finite rank operators. In fact, we can give the most canonical type of example, at least as far as self-adjoint operators goes. So example. So let's take H to be L2. So let's pick a sequence of complex numbers, lambda 1, lambda 2, lambda 3, so on. Then you can define a formal linear operators by this matrix, right? Lambda 1, lambda 2, lambda 3, so on, and 0, 0, right? So it's a notation. Sorry? I can't hear you well. I didn't hear what you said, sorry.
Masood, I had a question.
Yes, yes.
So in the space of bounded linear operators,
Yes.
being compact a closed condition?
You mean is it the set of compact operators closed? Is that what you mean?
Yeah.
Yes, it is. Yes. Because it's obtained as closure of something, so it's obviously closed, right? But I'm gonna write it down anyhow, so that's okay.
Thanks.
Thank you for asking questions. Any other comments or questions? Okay, so let's look at this operator. Now, you can just easily check that, first of all, T is bounded if and only if this sequence is bounded. In the complex plane is a bounded sequence. And second of all, you can show that using this result now, you can show that T is compact if and only if these lambda n's go to 0 as n goes to infinity. Right? So, well, this one, of course, it's basic Hilbert space theory. It's easy to prove using L2 norm and that stuff. So I don't mind. This one, now imagine lambda n goes to 0, right? Then you can take T to be limit as n goes to infinity of these operators. Lambda 1, lambda n, 0, 0, and then we have 0, 0, 0, right? Now, T is limit of these finite rank operators because lambda n is going to 0, right? This implies that you have this limit. But these guys are finite rank, right? So if lambda n goes to 0, you have written your operator as a limit of finite rank operator, so it's compact. So hence T is compact. Now you want to show the other way around also that, because that's an if and only if statement. If T is compact, then you can directly show that if this sequence lambda n doesn't go to 0, it's bounded, so it has a non-zero condensation point. Subsequence converges to that point, and then the compactness fails in that case. You can directly show by basic estimates. So, sorry. So this is this is a good example. Now note that in this example, of course, T is self-adjoint if and only if these lambda n's are real numbers, right? That's also very clear, but we're going to use it. Now, so there was this question about the set of compact operators being closed or not, and this sort of things. In fact, this lemma that I proved, the lemma that said that compact operators are limits of finite rank operators, it has a lot of consequences. So let me write some of them. So corollaries the lemma. Let me just prove. So there's a notation K of H, subset of, so my notation for all bounded operators is L of H, subset of L of H. So this is compact operators. The set of all compact operators. And this is the set of all bounded operators. Okay. So that's more or less a standard notation, although some people use B of H for bounded operators. I use L of H, so there are two notations. Use compact operators. So some of the corollaries of this lemma is that, first of all, this K of H is actually a closed two-sided ideal in L of H, right? Is a closed two-sided ideal in L of H. You see, we noticed in the last lecture, and it's quite immediate, in fact, that finite rank operators form a two-sided ideal. So these are limits of this two-sided ideal, and then elements from the two-sided ideal. So it is two-sided ideal. Everything here follows easily from the lemma or just basic from first principles. So keep this in mind. K of H is a closed two-sided ideal in L of H. I mean, for example, the sum of two compacts being compact. From the original definition, maybe it's not so obvious, but using the fact that compact operators are limits of finite rank operators, and finite sums of finite rank operators is finite rank easily by algebra. It just shows that they form a linear subspace, etc. So this is a one important result that we need. And another one is that T is compact if and only if T star is compact. So an operator is compact if and only if its adjoint is compact. I guess to prove this, it's enough by using that lemma again, it's enough to show that an operator is finite rank if and only if its adjoint is finite rank, right? So T is finite rank if and only if T star is finite rank. So using this and using the lemma, this follows. To prove this, you just need basic algebra. I mean, it follows easily. Okay. I guess that's it. So these are basic corollaries of this lemma. Now, this kind of presentation, this sort of finite rank, the compact operators that we discussed here in this model, in a way, it's universal in the sense that spectral theorem for compact operators says that all compact self-adjoint operators are of this form. So let me write it down. So a spectral theorem for compact self-adjoint operators. So this is the result that was basically proved by Hilbert in first decade of 1900, sometime around 1904 or something. So Hilbert, circa 1905, I would say, but I don't know the exact date, but Hilbert wrote several papers in that decade on functional analysis. Actually, he founded the theory of Hilbert space in that decade, he and his students. So that's, so what is the result? So theorem says that for any compact self-adjoint operator T, there exists an orthonormal basis EI, I from 1 to infinity of H, such that EIs are eigenvalues, eigenvectors of T. So then we can actually write this T as lambda 1, lambda 2, lambda 3, so on. So yeah, in that basis, EI, we can write the operator T in this form, in the diagonal form. These lambda i's belong to R because the operator is self-adjoint, and these lambda i's go to 0. And in fact, there might be a big corner here which consists of 0. So moreover, let me mention the multiplicity of non-zero eigenvalues is finite. Multiplicity of each non-zero eigenvalue is fine. But of course, 0 eigenvalue might have infinite multiplicity because the operator could be completely 0. In that case, it's just zeros on the diagonal, nothing else. So it can. So 0 can have infinite multiplicity, but non-zero eigenvalues cannot have infinite multiplicity. So can you tell me why non-zero eigenvalues do not have infinite multiplicities by any chance?
I mean, lambda n has to go to 0, right?
Sorry?
Lambda is have to go to 0, right?
Yeah, but it follows from this actually, right?
Okay.
You have a non-zero, infinitely repeated eigenvalue, you're never going to get a finite rank approximation.
That's right. If there is a non-zero eigenvalue, so the operator is acting like non-zero multiple of identity on that subspace. If that subspace is infinite dimensional, then it's not going to be approximable by finite rank operators in that subspace, but it's just constant lambda identity, so cannot be approximated. So yeah, that's why we can never have non-zero eigenvalues of infinite multiplicity. So as a result, well, I mean, yeah, maybe it should have been formulated in a rather different way, but the idea is that as a result, these non-zero eigenvalues are going to 0. Okay, so the model of compact operators that we discussed, at least in the self-adjoint case, is universal. They're all of this sort. And that's Hilbert's spectral theorem for compact self-adjoint operators. So the idea of proof is very interesting. You see, you have seen the spectral theorem for matrices, self-adjoint matrices, for example, in linear algebra. Well, that proof doesn't work here. Let me tell you why. So proof. The proof starts by giving one specific eigenvalue, actually, for the operator. First, show that either a norm of t or minus norm of t is an eigenvalue. Of t. Right? So that's a crucial step in order to prove the result. Why? Let me convince you that if you prove this, then you're done. You see, either norm of t is equal to 0, in that case t is equal to 0, so there is nothing to prove, so you have 0 zeros under that. Or norm of t is not 0, right? In that case, then you have a non-zero eigenvalue with finite multiplicity. So then what you can do, so assuming this, so then let W equal to eigenspace of eigenvalue W. Sorry, eigenvalue norm of t or minus norm of t. Then, because the operator is self-adjoint and this space is finite dimensional, you can decompose the space into orthogonal direct sum of two subspaces, right? So then you can write A is equal to W direct sum W perp, and W and W perp, orthogonal things, is invariant under T. Now, this norm of T or minus norm of T, they are not just any other eigenvalues. They are indeed eigenvalues of maximum length for T. So all other eigenvalues have length less than this thing. That's easy from the definition of norm, you can see. Since norm of T is the maximum possible length of an eigenvalue for t. So if you look at t restricted to this one, it's again a compact operator. It's self-adjoint, and its maximum eigenvalue is going to be smaller than what we have here. So basically now what I'm saying is that we can repeat the process for this. Can repeat the argument. So there is a kind of infinite process. Each time we are going to get eigenvalues which are smaller. It could be negative or positive, but in length they're going to be smaller and smaller. At one place you're going to exhaust the whole space. That's the rest of the argument is just basic things. So we can repeat the argument to finish the proof. So I just put it like this. So this step is quite similar to finite dimensional linear algebra proofs that you learn in undergraduate courses, right? But there, to start the process, you have to use the fact that your operator has an eigenvalue. In order to do that, you just write this characteristic polynomial, and then because you're working over complex numbers, then so every polynomial has a solution over complex numbers, so you can start your induction process. But here, of course, we don't have that tool, right? In infinite dimensions, we don't have characteristic polynomial just like that, right? So in order to start the process, you had to use some abstract arguments like this. And this was what was devised by Hilbert and his school. That's what functional analysis is good for. A lot of times you just replace those characteristic polynomials and finite stuff by some slick, nice argument like this. Existence of this one. Okay, now to prove the first step, okay, so this is the rest of the argument if you know the proof. So to show the first step, what we can do is it's enough to show that the norm of t squared is an eigenvalue of t2. Then here you use compactness because this is norm of t squared. So you can approximate norm by a sequence, by norm of t squared by norms of sequences of vectors inside the unit ball, say, using definition of the norm. And then you just pick a convergent subsequence for that sequence of t of x n's using compactness. And the limit of that convergent subsequence gives you the eigenvector that you need. So that's the idea of the proof. So I just expressed it like that. So I won't write it. So just goes like that. So this is stuff you can read in many books. Again, Lax is a very good reference. So you can just read all these proofs in Lax functional analysis. Or many other books or notes. Okay, so this spectral theorem for compact operators is pretty important indeed. Okay, so any questions or comments? Okay, so now let me define a class of operators that gives us compact operators, and they have some interesting properties. So this is the Hilbert-Schmidt operators. So I will give examples of these things. They can be defined in a more abstract fashion, but let me just give you the basic examples. So now let's assume H is equal to L2. So now let's look at, take an operator T such that in this standard orthonormal basis, we can write it as, I mean, my notation is going to be basically Aij. I from 1 to infinity, j from 1 to infinity. Such that the Hilbert-Schmidt norm of the T, which is by definition equal to some absolute value of Aij squared. So it's L2 norm of this sequence. Ij from 1 to infinity is less than infinite. Okay, so this is the definition of the operator. Now it's easy to check that then T is a bounded operator. And in fact, the norm of T, which is the operator norm of T, is less than equal to Hilbert-Schmidt norm. So Hilbert-Schmidt norm is always bigger than or equal to norm of T. I mean, to see this, well, I mean, you just have to do the basic estimates, but a simple example could be something like this, maybe. Take T to be 1, 1/2, 1/3, so on, 0, 0. Then this T belongs to Hilbert-Schmidt, right? Because norm 2 T squared, what is this guy? Is some 1 over n squared. This is less than infinite. So this is a compact operator, as we know. It's also a Hilbert-Schmidt operator by this definition, as we know. And can you tell me what is the operator norm of T? For those who are maybe fresh on functional analysis, you just took functional analysis course. It doesn't matter, just have a guess, that's okay.
1.
It's 1, yes. In fact, the maximum here is what you have, right? That's and of course it's strictly less than Hilbert-Schmidt. So in general, if you have a diagonal operator, the operator norm is going to be sup of absolute value of these guys, but here the Hilbert-Schmidt norm is going to be square of those things and then taking the square root of those things. So just
Masood, when does equality ensue?
Yeah, I mean, in this case, equality really holds if and only if it's just a rank 1 operator.
In general, do we have a criterion?
In general, I'm not sure. No, I don't. There must be, but I'm not aware of. But I guess rarely it happens, but yeah, that's a good question. But yeah, but I mean, just think of this sort of examples, and then you know that they're really. But now the point is this: in general, any Hilbert-Schmidt operator is compact. That's what I wanted. I'm getting it. So the lemma is that T Hilbert-Schmidt implies that T is compact. And the reason for this is that we can approximate T by finite rank operators. Proof. You just notice that T is equal to limit of, here you put all aij's that are you have, and then you put rest equal to 0. This operator is obviously, so here is n and up to n. So in operator norm, because this guy is Hilbert-Schmidt, the remainders are going to 0. So then, okay, then it follows that it's really a norm limit of this finite rank operators like that. So, so by our lemma, T is compact. I mean, this guy is finite rank, right? Okay, so if it wasn't Hilbert-Schmidt, you could have had, for example, 1, 1, 1, 1, 1 here, all the way up to infinity. That would be identity operator, right? If you cut it down, you're going to get identity here, but then you still have 1 in the remainder. So that's not going to approximate approximable by finite rank operator. So that's not. But in this case, Hilbert-Schmidt. So now this Hilbert-Schmidt is. So there is some nice notation for Hilbert-Schmidt. So we have these compacts. So maybe I should just write compact operators H. And then we have inside L of H. Here, it properly contains finite rank. Of course, this contains 0. And then there is a sea of, there's very, very interesting world of operators living there. We just looked at one of them, which is this Hilbert-Schmidt. So this will be denoted by L2 of H. I use the notation Hilbert-Schmidt, but is also, L2 is more standard. So this is Hilbert-Schmidt. Okay. And these containments, of course, assuming H is infinite dimensional, these containments are proper, right? So there is one more thing here which you should be aware of later on, plays an important role, and that's trace class operators. That's L1. I'm going the other direction. I'm sorry. Sorry. So here is K of H. Properly contains L2 of H. And this L2 of H properly contains L1 of H. Okay, so L1 I did not define. We will come back to that later on. This is trace class operators. These are Hilbert-Schmidt operators. These are all compact operators, and that's these are finite rank operators. So this we checked is an ideal. This is an ideal. All these guys are going to be two-sided ideals. This is closed. These guys are not closed. This is not closed. So that's the situation so far. Okay, now these Hilbert-Schmidt operators are obtained, as I said, there is an abstract definition of L2, sorry, this is L2 maybe, which I don't give right now, but they have a different incarnation in terms of integral operators. So, and that's actually how this Fredholm theory started. And that's what we need later on. So let me just mention this. Integral operators. So in this case, we just take H to be equal to, I mean, you can take more general spaces. We will do that, but let's just take L2 of AB, some interval, right? And let's take K of XY. I mean, I just write K of XY, but really it belongs to continuous functions on interval cross interval. Okay, so it's just a function of continuous function of two variables. Each variable is in this interval A and B. Right? Then this defines an operator, right? Tk from L2 of AB to L2 of AB. So that's the integral operator defined by this kernel like this. Tk f at x is equal to integral k of xy f of y dy from A to B. So this is what we learn, you know, even in undergraduate courses as integral operators. You see, it's really like a matrix, right? It's a kind of continuous matrix. You know, there are two variables, x and y. Matrix have I and j, and sum is turned into integration. Otherwise, it's like a matrix acting on this column vector f of y, but y is a continuous variable. So it's a continuous matrix algebra in some sense. Anyhow, so the basic thing is this lemma is that if f is continuous, then Tk is a Hilbert-Schmidt operator. I mean, so let me say it's a compact operator for now. Okay. So if f is continuous, then Tk is a compact operator. Now, proof of this, we can uniformly approximate f. So f is a continuous function of two variables by simple types of functions. So approximate, I just write it like this, approximate f by functions which are of this form, fi of x, gi of y, I from 1 to n. By such functions, okay? we can do that using basic approximations, or I mean, this is quite obvious. I mean, we can do that. So then, if your function is of this form, say fn, you notice that if your kernel is of that form, or maybe I should say kn, sorry. Because it's a function of two variables, is a kernel. So k is equal to limit of kn. goes to infinity uniformly. But now if you look at T of Kn, what do you see? So this T of Kn is, in fact, a finite rank operator. Because if you go through this process, replace K by Kn, you can, there are these integrals gi of y, f of y to calculate. Everything is written as linear combination of these n functions f1 up to fn, right? So it's a finite rank operator. But T of K is a norm limit of T of Kn's. So it follows that T of K is compact because these are finite rank. Is limit of finite ranks. Is a limit of finite ranks. So is compact. Okay, so this is a very good example, a very important class of compact operators that are obtained as integral operators with continuous kernel.
Masood, I don't know. So I have a question.
Yes, yes.
So when you say if f is continuous, then tk is compact, are you restricting tk to the space of continuous functions?
TK, no. I mean TK. What happens? Look at. I mean TK goes from L2 to L2, right?
Right.
I mean it goes from Hilbert space to Hilbert space. But
yeah.
Now, if K is Kn, I want to make sure that we understand that T of Kn is a finite rank operator, right? Why T of Kn is a finite rank operator? Let's see what happens. If you replace K by Kn, which is here, you see this part?
Mm-hmm.
Okay, so then what happens to this integral? This integral can be written, so let me write it in this case. Kn f at x is integral a to b sum fi of x, right? Gi of y.
Oh, no. So in the sentence, in the first sentence of the lemma that you have written, you mean if Kn is continuous, not if f is continuous.
K is continuous, right.
Oh, okay.
Yes,
Okay, yeah.
yes.
Then I understand. Okay.
Thank you. Very good. Yeah. Thanks, Bruno. Yeah, no, indeed. If K is continuous, very good. If K is continuous, then great. Okay, so then of course you can write everything in terms of linear combinations of FIs with some coefficients which is obtained by integrating G of y against F of y. So some linear function of finite number. So this is okay. So should I finish this, or you're fine with this? Fine with this argument?
Yeah, I'm fine with it. Yeah.
Okay, very good. So we are done again. Good. So as I said, you can extend this idea vastly. I mean, so in general, this idea works like this. You can take H to be L2 of X, say X a locally compact Hausdorff space, for example. And we can take, so let me just take compact Hausdorff space to make life for myself a bit easier. Compact Hausdorff space, and you can take K, a continuous function of two variables. So it's a continuous function of x cross x, right? Then you can take this integral operator TKF. So TK goes from L2 of x to L2 of x. So So of course we have to assume there exists a measure in order to take x2. So x is a compact Hausdorff space. Mu is a Lebesgue measure. I mean, yeah, no. I mean, it is a measure. Whatever. X and mu is a measure space, but X happens to be compact Hausdorff space. Then this TK from L2 of X to L2 of X is the integral operator, which again is defined completely like before. I mean, there's no difference. But this time we just integrate over the whole space X, K of X and Y, F of Y, dy, right? Everything goes through, and then you have the basic result that this integral operator Tk belongs to compact operators on L2 of X and mu. But as I said, in fact, more is true. This, in fact, belongs to Hilbert-Schmidt operators. In fact, Tk belongs to L2 of X and mu. So notation is a bit funny, but this is Hilbert-Schmidt operators of this Hilbert space L2 of X and mu. So this I give it as an exercise. It's important to know that this is Hilbert-Schmidt actually. And what is true is that the Hilbert-Schmidt norm of this guy, so that's important to know that the Hilbert-Schmidt norm of Tk, that's square, is equal to integral of K of xx, K of xy, sorry, dx dy, absolute value squared over x cross x. So it's a double integral, K of xy squared dx dy over x cross x. That's the Hilbert-Schmidt norm in this case. You can prove this by picking an orthonormal basis in X, and you go from there. So it's a good exercise to think about these abstract integral, a little more abstract integral operators.
Is it easy to see in general that this is not Fredholm?
Well, it's very easy. I mean, these guys are never Fredholm actually, as we'll see now. So that's completely the opposite side of the universe, right? It's like North Pole and South Pole. They are totally separate. The two worlds are totally separate from each other. Fredholm and compact operators.
Okay.
In fact, this is a good point to start Fredholm operators discussions, because we just discussed compact operators in the context of Hilbert spaces. Now it's time to discuss these Fredholm operators. Sorry. I mean, any questions or comments about this so far? I mean, any other questions? So we had some good questions. That's very good. Okay, so these compact operators are almost zero operators, as we discussed last week. Now we are going to discuss Fredholm operators that are almost invertible operators, and that's what this next definition is all about. So a bounded linear operator T from H to H is called Fredholm if, well, the definition exists exactly like the algebraic case that we did, without any difference. If dimension of kernel of T and dimension of co-kernel of T are both finite. So the definition in this analytic situation, in the Hilbert space situation, is no different than the purely algebraic situation that we had before, right? So that's exactly the same definition. And then in that case, we can define index of T and define its index as before, the same definition, dimension of kernel of T minus dimension of co-kernel. Right? So that's the thing. So okay, so it looks like we have gained nothing over algebra definition. It's purely same definition exactly. So, we have these compact operators, which is very different compared to finite rank operators, and that's going to help us to decide which operators are going to be Fredholm or not, based on in a much easier way than the algebra case. Now, any questions about this so far? Now, one of the things about this Fredholm, one of the first things to know is that the image of a Fredholm operator is closed. That's one of the most fundamental properties we need to know. Lemma. Is that T Fredholm implies that image of T inside H is closed. Okay, first of all, image of T is closed. And T defines a linear isomorphism. An isomorphism from kernel of T, orthogonal complement to image of T. In particular, if you look at T inverse from image of T, in particular, so T inverse from image of T to kernel of T orthogonal. I mean, not T inverse did not exist, but T inverse in this sense, restricted to image of T. I mean, from image of T to kernel of T perp is bounded. So the crucial thing is to show that image of T is closed. That's not obvious at all.
Is it also Fredholm?
Sorry?
Is the inverse also Fredholm?
The inverse, I mean, in this, well, a Fredholm operator doesn't have to be invertible, okay?
No, but when restricted to image T.
So, because now if you restrict it here, so, I mean, from image of T to kernel of T orthogonal, you're going there. This is an isomorphism, so then it is.
Oh, it's an iso. Sorry, yeah. Okay.
Isomorphisms, invertible operators are. Maybe I should mention. Actually, no. I mean that was a good question. So here's an example. Of course, I mean here, like if T is an isomorphism, then of course T is Fredholm. Because in that case, as we saw last week, dimensional kernel and co-kernel are both 0, and index is equal to 0. So isomorphisms are definitely, I mean, bounded invertible operators are definitely Fredholm, but not vice versa. And so, okay, good. But that's a good question. Okay, so so let's prove this, because that's a kind of very crucial lemma, really. So since image of T inside H, I mean, by this condition of Fredholmness has, I mean, it's finite codimension, right? Has finite codimension. Can pick a finite dimensional subspace such that image of T plus T of H is equal to all of H. We just find a complementary subspace, not necessarily orthogonal or anything, just a finite dimensional subspace, right? Such that H is equal to T of H direct sum V. This direct sum, as I said, is not an orthogonal direct sum, it's just an algebraic direct sum, right? So define a map from kernel of T orthogonal, perpendicular, direct sum V to H by sending X and Y to X plus Y. Now, if you look at this map, it's algebraically is an isomorphism. Is an isomorphism and is bounded. Bounded because this operator yeah, so I think I made a mistake somewhere. I should go to T of X here plus Y, because I'll go to image of T, and then this decomposition tells me that, yeah, I should go to T of X. So, okay. It's bounded because T is bounded, and here we are not doing much, so boundedness is preserved. So now here is a beautiful result from functional analysis. If you have an invertible, algebraically invertible operator from Hilbert space to Hilbert space that's bounded, then its algebraic inverse, which exists, because we are assuming it exists, is also bounded. So it has a bounded inverse. So its inverse bounded. So that's very nice. So the inverse is going to be the map from H to kernel of T perp direct sum V. So it gives a bounded isomorphism. Isomorphism between kernel of T perp and image of T. Because there's an isomorphism between these two subspaces by bounded linear operator. This is closed, so it follows that this is closed. This part is closed. Okay, so the image is closed. Okay, so that's the end of it. So here we had to use analysis, some basic functional analysis, some very, very basic Hilbert space theory, but still, we couldn't do without it. Now, to appreciate this result, I want you to think about, to give an example of an operator whose range is not, whose image, range is not bounded. Is not closed. So just to appreciate that this Fredholmness is a very, very strong property. So exercise is this. Bounded such that image of T is not closed. Okay. So can you think of an example offhand like that? Or? Okay, so that's a good exercise then. Okay, very good. So I think it's good to think about this exercise to appreciate the power of this result that we proved here. Now, one of the things now to understand is index zero operators, to understand when an operator is index zero. So that's the context of this proposition. I just say index of T is equal to 0. So I should say T is Fredholm and its index is equal to 0 if and only if T is equal to S plus T0 with S invertible and T0 compact. So that's a very nice result. It characterizes index zero Fredholm operators. Index zero Fredholm operators are those operators that are of the form S invertible plus compact. Invertible plus almost zero operators are going to give us index zero Fredholm operators. So proof. We just use this lemma that we proved. So consider this diagram. Kernel of T perp takes some kernel of T. So that's the orthogonal decomposition of H. We go to image of T. Direct sum, image of T, orthogonal complement. You see, now this is closed. So if I take its orthogonal complement, I get a finite dimensional subspace whose dimension is the same as dimension of kernel of T because index is 0, right? So then the map is defined like this. Here, I just go by this operator, just T. And from kernel of T to this, because they have the same dimension, I just fix a linear isomorphism. So S0 is any linear iso. I know that this exists because this dimension of kernel of T and dimension of image of T orthogonal complement are the same because we are in the index 0 case, right? So fix that. Okay, now let us define operator S to be like this. Okay, so let S be equal to T, and when it's restricted to kernel of T, orthogonal complement, and S, so restricted to kernel of T orthogonal complement, and S equal to S0 on kernel of T. Or on, right, on kernel of T. So, so it's an isomorphism. By the way, we chose this. S is an isomorphism. I mean, bounded linear isomorphism. Now let T0 be equal to restricted to kernel of T, orthogonal complement be equal to 0, and T0 restricted to kernel of T be equal to minus S0. Then T equal to S plus T0. Okay, so that shows that if you have an index 0 Fredholm operator, you can always write it as an invertible plus a compact operator, right? T0. In fact, we can always write it as invertible plus a finite rank operator, but anyhow, I just claim this compact case. Now, conversely, still we have to prove the converse statement. Assume that T is equal to S plus T0 now. But S is invertible and T0 is compact. We want to show that T is Fredholm and its index is 0. So that's not obvious, right? Then have to show T is Fredholm and index of T is equal to 0. Well, but this S is invertible, right? So this is suffices to show if you multiply this by S inverse, the Fredholmness doesn't change at all. So if you prove S inverse of T is Fredholm, then you have proved that T is Fredholm. Index of S inverse of T is the same as index of T because you're multiplying by an invertible, by an isomorphism. So that's equal to 1 plus S inverse T0 is index 0 Fredholm. Right? So we just have to show that for operators which are of the form identity plus a compact operator, they are index 0 Fredholm. So this is the identity plus compact now, right? Because compacts form an ideal. So identity plus compact. So that's equal to 1 plus k, say. So then what we can do, we can approximate this compact by a finite rank operator and an operator whose norm is less than 1. So write k is equal to maybe k0 plus f, where k0 is finite rank and norm of f is less than 1. Okay, so then the whole thing, so again, I just give the main idea without going into too much detail. Then we just have to use the fact, then use geometric series. To invert operators of the form identity plus f. Such operators, if norm of x is less than 1, they're always invertible. So you can just use this series. So 1 plus f inverse is geometric series is sum minus 1 to I suppose I from 1 to infinity. Yeah, so this looks okay, right? So is invertible. So once you can invert this 1 plus f, then you can continue the argument, and the rest is not difficult. So I won't write down the all the steps. So just maybe when you are in my office, we can go through the proof together sometime. But right now it's okay. Any questions? So. Okay, so this result is very, very important, I should say. I mean, yeah, that's an important result. So, for example, now we are going to touch base with actually what really Fredholm proved, and that's why these operators are called Fredholm operators. So let me tell you. This is the famous Fredholm alternative. Well, basically, we have proved it. So Fredholm alternative. So this is this goes back to really Fredholm himself, 1900. He worked with the case where K is a compact operator that's defined as an integral operator. He and others were really only interested in integral operators, and which are compact operators, then 1 plus integral operators, things like that, and eigenvalues of those. So those operators are of this form. So what he showed is that well, in this modern language, really, he didn't prove it in this context. He proved it in very, very concrete context of integral operators again. But essentially, is this, that for any k compact, I plus k is Fredholm, and index of I plus k is equal to 0. That's what we proved, right? Here is what we did. But in particular, you can derive the version that was formulated by Fredholm was that for any lambda different from 0, it's formulated like this. For any lambda different from 0, k minus lambda I either has a has kernel 0 or is invertible. So if lambda is different from 0, you can factorize here, then you get something essentially of the form identity plus compact. So basically the result says that if its kernel is 0, I should say non-invertible in this case. You see, because it just says that if the kernel of this operator is 0, then it has to be onto, because it means that it's co-kernel also, because index is 0. You see, index of I plus k, this is 0, right? So this is equal to dimension of kernel of I plus k minus dimension of co-kernel of I plus k. So this is 0. If this guy is 0, then this is 0. And if this is 0, then this is 0. So that's the alternative. Okay, so Fredholm alternative really for us, it's just the statement that if you have a compact operator, identity plus k is Fredholm and its index is 0. So either its kernel is 0 or otherwise cannot be surjective. So there are some operators that are missing. It's not invertible. Well, that's not, I don't know, I don't like this statement very much. It's not surjective. I never thought about it in terms of eigenvalues. So any questions or comments about this? Okay, so yeah, this is heavy today. So is it okay if I just continue for maybe another 10 minutes before 3:45, 3:45 we finish? Is that okay?
It's fine by me.
Sorry?
It's fine by me.
Oh, okay, good. So now we mentioned Atkinson's theorem in the last lecture. Now here is the version of Atkinson's theorem that we actually need. Again, is really a fundamental result. So let me write it. So theorem Atkinson. It basically tells us when an operator is Fredholm. Gives us very nice criteria for being Fredholm. So T is Fredholm. If and only if, so maybe I would say if and only if T is equal to, so I would say T is invertible modulo compact operators, or I would say modulo finite rank operators first. If and only if T is invertible modulo compact operators. So, well, in both cases, modulo finite rank or modulo compact, it really means, i.e., there exists S such that 1 minus TS and 1 minus ST are both compact. And in this case, of course, means that there exists an S such that 1 minus TS and 1 minus ST are both finite rank operators. So being invertible modulo finite rank or being invertible modulo compact are equivalent. So this S is called, as I said last time, it's called the quasi-inverse or parametrics for T. It's a parametrics. Depends on the context. In PDE, it's called parametrics. In more algebra, it's called pseudo-inverse or pseudo-inverse. Of T. Of course, S is not unique. If you find one, then you can find many. So, so this is Atkinson. So the proof is not difficult now. So let me just mention. So this is an alternative formulation that's important. Of Atkinson. So we have this two-sided, close two-sided ideal, right? K of H, right? Inside L of H. So this is a close two-sided ideal of this algebra. I can go to quotient algebra. And this goes to 0. Okay. Now, this is an exact sequence of algebras. In fact, it's an exact sequence of C-star algebras, right? Because everything is on the level of C-star algebras. It's an exact sequence of C-star algebras. So, well, I mean, obviously this is an algebra, but I mean, in C-star algebra theory, they prove that if you have a C-star algebra, you mod out a closed two-sided ideal, then you're going to get a C-star algebra again. So this is a C-star algebra too, and it's unital. It's obtained by dividing all operators by compact operators, right? So Atkinson really says, so let's take pi. So Atkinson really is saying this, that Fredholm operator, so let me put it like Fred of H, is equal to pi inverse of the group of invertible elements here, right? So I just write it as K of H divided, oh sorry, L of H divided by K of H. So this just means the group of invertible elements. So this is an infinite dimensional Lie group. I mean, huge infinite dimensional group. It's a group of invertible elements in a C-star algebra. So a lot is known about such infinite dimensional groups, and a lot is not known still. So that's a very, very interesting group. It's infinite dimensional. And so Fredholm operators is just inverse image of such things here. And here, I mean, that's the last statement formulated in this language, right? So, yeah. So it's just a second. I will. Sorry about that. So, yeah, this algebra, by the way, has a name. The person who introduced it and studied first is Kalkin. It's called Kalkin algebra. Okay, so the group of invertible elements in the Kalkin algebra is exactly the image of Fredholm operators. Okay, so proving this, all these equivalences, now we know what to do. So proof. Of course, we can always decompose space. I mean, certainly from kernel of T, orthogonal complement to image of T is an isomorphism, right? So imagine we want to prove that if it is compact, then it is invertible modulo finite rank operators. The first statement. This is the image of T is an iso. So let S from image of T to kernel of T perpendicular be this T inverse. So S equals to T inverse restricted to image of T, which you know it exists over there. And let's assume S restricted to image of T complement, orthogonal complement. On this finite dimensional subspace, you define it to be 0. Then ST is equal to 1 on this huge space, kernel of T orthogonal complement. And ST restricted to kernel of T is 0, of course. Right. And then you can easily see this is equivalent to saying that 1 minus ST and 1 minus TS is finite rank. Both are finite rank. Or finite rank. So then you can also prove that, of course, if it is finite rank, then it is invertible. If invertible modulo finite rank is invertible modulo compacts, because finite ranks are compacts. So now the last statement to do is to go from invertible modulo compacts to being Fredholm. And that's not very difficult either. So I'll just leave it. I mean, there are details to verify, but details are written in many, many places. So. Now, this has really beautiful properties, I mean, consequences, this result. So, we're kind of now getting into so then we can prove that T Fredholm if and only if T star is Fredholm. In fact, you see, you have this equation 1 minus ST finite rank, T Fredholm 1 minus TS finite rank. If you adjoin this thing, you have 1 minus S star T star and 1 minus T star S star. Again, I said that adjoints of finite ranks are finite ranks. That's pure algebra. So these are finite rank. And okay, so then it means that T star is invertible modulo finite rank operators. So using Atkinson, we know that T star is Fredholm if T is Fredholm. Of course, the other way around is the same proof because T star is T. So there's nothing to prove over there. So to show that adjoint of a Fredholm is interesting that we needed this Atkinson, which is not so bad. But then the index of T star, if you look at index of T star, well, I mean, that's equal to minus index of T. Again, I give this as an exercise to, it's important to do the exercises. So, okay. Now we are getting to kind of zooming into the space of Fredholm operators, and we want to understand its topology a little more. So, because that's where most of beautiful stuff is hidden for us. That's the topology of the space of Fredholm operators. So one of the things, first things, so let me just write it like this. Topology of Fred H. So by Fred H, of course, we mean space of Fredholm operators inside all bounded linear operators. So yeah, L of H itself, of course, is a linear space. Is a normal linear space. But this guy is not a linear space. It's a subset of this linear space L of H. And gradually we have to understand its topology. It has a very, very interesting topology. But now we are just looking at very first steps in topology of this guy. So the first result really is this lemma. Fred H inside L of H is open, and index from Fred H to L of H, no, sorry, to Z. Z is a continuous map. All right, so that's right. So that's what we want to know. Okay. So let me just give some ideas about the proof of this. Actually, let's prove it. So if we look at pi, the projection map that I just erased, from L of h into this Kalkin algebra L of h divided by K of h. One of the things that one learns in basic Banach algebra theory and sister algebras is that basically I have my battery dying soon, so I have to finish. So why don't we finish right now, and then, because my battery is dying, sorry, I don't have a plug here, so I mean my cord is not long enough. So anyhow, so we'll finish right now. So we just use this map. We notice that the group of invertibles in a Banach algebra is an open subset of that Banach algebra. Pi is continuous. Its inverse image is going to be open again. So that gives us openness of Fredholm. There is another proof that I can give, but and then continuity of index, we'll think about it because it's an integer valued function and it's going to be constant on the components. So we'll look at it. Okay, guys, thank you. If you don't have any questions, or maybe you have questions, ask, please. Okay, so I'm going to stop the recording, then we can maybe discuss your questions.